Okay, energy. Energy is a major component of our universe. There's matter and there's energy. Those are the two big things. Scientists define energy as the capacity to do work. And then we also define work as the result of a force acting on a distance. So this is different than the definition of work that we use in everyday life. So if I take this bottle of Simple Green and I push it across the counter, I did work. Now, you probably can't find anybody to give you money to pay you for doing that, right? So that's not going to be anybody's job, anybody's work, pushing a bottle across the counter. But in science, that is work. So energy is the capacity, the ability to do that. The behavior of matter is driven by energy, and that's why, although chemists are mostly interested in matter, energy affects how matter behaves, and so we need to understand energy at least a little bit. So matter is conserved, energy is also conserved. So in a chemical reaction, energy is neither created nor destroyed. You can't make energy out of nothing, and energy cannot disappear into nothing. The balances do this adjusting thing, and they kind of sound like deranged cows, right? And so it's like, what the heck's going on over there? It's just the balances being weird. So the total amount of energy in the universe is constant. You can change energy from one form to another. You can transfer energy from one object to another, but you can't create energy. There are different kinds of energy. Kinetic energy is energy associated with motion. Something that's moving has kinetic energy. Potential energy is energy associated either with position or composition. So, marker. So if I hold this marker up above the floor, it has potential energy. Because if I let go of it, that potential energy can be turned into kinetic energy and it'll fall to the floor, right? Yep, just as predicted. So its position gave it potential energy. You can also have chemical energy. This is a form of potential energy. This is the energy associated with the composition, and that has to do with the relationships between the particles that compose the matter. So gasoline is flammable, right? You can burn it and it gives off heat. Gasoline has stored potential energy in the form of chemical energy. Electrical energy is associated with the flow of electrical charge. Thermal energy is actually a type of kinetic energy. We talked about solid matter and how the particles in a solid are not actually completely still. They're vibrating, just like students sitting in chairs are moving a little bit. That movement is kinetic energy, and that's the energy that's associated with the temperature of a substance. It's thermal energy. So kinetic and potential energy are the main categories of energy. The total energy of any sample of matter is the sum of its kinetic and potential energy. So here we have an illustration of a reservoir with a dam. Behind the dam, the water has high potential energy because if it's released, it will flow down, right? And that potential energy gets converted into kinetic energy as it flows. Down here, on the other side of the dam, where the water is lower, the water has lower potential energy. And so we can use the difference in potential energy there to generate electricity. We can use the kinetic energy of the water as it's moving to generate electricity. But when it's just sitting there, it's just potential energy. So energy is something that's measured, and so we have to have units for it. So the metric unit, the SI unit for energy is the joule. That's a J. It's a weird font that makes it look strange. Joule, and the abbreviation is capital J. Another unit of energy we use frequently in chemistry is the calorie. Now there are two kinds of calories. This is a calorie with a lowercase c, and then there's a nutritional calorie, which is written with a capital C. That can be confusing. Sorry, it's just how it is. A capital C nutritional calorie is actually 1,000 of the small c calories, or a kilocalorie. And a calorie is defined as the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. From your textbook, you have a nice little table of energy conversion factors. I don't expect you to memorize the relationship between calories and joules. I would expect you to know the relationship between calories and kilocalories, because that's a metric prefix that you should know. Kilowatt hours is used by PG&E to measure the energy you use in your home. That unit could come up in some homework problems, but we don't generally use that in chemistry. So it's in there, but we don't use it very much. So using the relationships between the energy units, we can do energy unit conversions. So the complete combustion of a small wooden match produces approximately 512 calories of heat. How many kilojoules are produced? Well, we're going to need a relationship. Here we have calorie is 4.184 joules. So we're going to need that. So make a note of that. 1 calorie equals 4.184 joules. So the problem only has one number in it. Let's write it down with its unit, 512 calories. That's a lowercase c. And the question is, how many kilojoules? So we need to convert that to kilojoules. We looked up this relationship between calories and joules, but that doesn't give us calories to kilojoules. But we can convert calories to joules. And then, can we convert joules to kilojoules? Yeah. It's the same process as meters to kilometers, or grams to kilograms. So we can do that in 2 steps. So 512 calories. We have 2 arrows, so we need 2 fractions. Calories to joules to kilojoules. Previous unit goes in the denominator, so they cancel out. We get all the units in place first, and then we put numbers in. So the joules to calories, that's a conversion we looked up. 1 calorie is 4.184 joules. And kilojoules to joules involves the unit, or the prefix kilo. Kilo means 10 to the 3. So I've got kilo on top. I'm going to write what it means on the other side of the line. 1 kilojoule is 1 times 10 to the 3rd joules. We've got 512 times 4.184 divided by 1 EE3. I'm looking at my starting number. It has 3 significant figures. This would be 4, and that one's exact. So we'll go with 3 sig figs. 2.14. I'm writing down 2 extras because that's what I do. So 2.14 kilojoules. Any questions? He was weightless. Okay.